Water is the most studied molecule on Earth, and yet for decades we couldn't answer a surprisingly simple question. When water gets squeezed into really narrow gaps, just a few molecules wide, inside battery membranes, biological channels or nanoscale devices, does it become more or less reactive? Experiments and theory kept giving contradictory answers, and it wasn't clear how to reconcile them.
In our work, we use AI-powered simulations to finally crack this. And what we found is that this previous disagreement came from comparing systems that were not at the same thermodynamic conditions. Once you do this comparison properly, then everything starts to make sense. To illustrate this, let's take water, for instance, trapped between two-dimensional sheets like graphene. These sheets are attracted to each other, and so they exert gigapascal pressures into the water that are pressures so high that you can find them deep inside the earth. And so this alone makes this water far more reactive. So now if we want to compare the reactivity of this type of water and bulk water, it is not a fair comparison. It is only once we start to take the differences between these two that actually everything falls in one place and this disagreement disappears.
But pressure is not the whole story. The confining material matters too. In boron nitride, the walls chemically bond to the products of water splitting, making the reaction even more favorable. Graphene, being chemically inert, doesn't do that. So rather than just shrinking pore size, we can choose materials whose surface actively participates in the chemistry. That gives us control to deliberately engineer water reactivity at the molecular scale for batteries, fuel cells and catalysis. And that is something we are really excited about.